Something unusual is occurring with Earth's magnetic field, causing concern for NASA. A significant area of reduced magnetic intensity has emerged between South America and Southwest Africa, resulting in an unusual dent in Earth's magnetic field that is expanding and bifurcating. This anomaly, termed the South Atlantic Anomaly, has puzzled scientists for quite some time. But what exactly is causing this expansive region of diminished magnetic intensity? Why is it imperative for NASA to monitor this anomaly? And perhaps most crucially, does the South Atlantic Anomaly have any impact on life on Earth? Stay tuned to find out. The magnetic field surrounding Earth serves as a crucial barrier, shielding us from the barrage of high-energy particles hurled from the Sun, thereby nurturing life on our planet. Without this protective shield, Earth could resemble the barren landscape of present-day Mars. Unraveling the origin of Earth's magnetic field involves delving into a complex interplay of various mechanisms and ongoing sources. Among these, the geodynamo process emerges as a pivotal player. This process requires specific prerequisites for a planet to generate a magnetic field. Firstly, the planet must spin rapidly on its axis. Additionally, it needs to harbor a conductive fluid within its core. Moreover, there must exist an internal energy reservoir propelling convection currents within this liquid core. Fortunately, Earth ticks all these boxes, meeting the necessary conditions for the geodynamo process to operate seamlessly. Deep beneath the Earth's surface, extending thousands of kilometers down, lies a vast reservoir of molten iron nestled within the outer core. With the planet's rotation, this liquid iron undergoes movement, setting off electrical currents that give rise to Earth's magnetic field. This magnetic field, in turn, triggers more electric currents, resulting in the generation of supplementary magnetic fields. Thus, a self-sustaining cycle of electric currents and magnetic fields within the core is established. Yet, Earth's magnetic field is not consistently uniform. Deep beneath the African continent, approximately 2,900 kilometers below the surface, exists a massive deposit of dense rock known as the African Large Low Shear Velocity Province. This enigmatic structure is the underlying cause of the South Atlantic Anomaly. Large Low Shear Velocity Provinces, LLSVPs, represent colossal formations nestled deep within Earth's mantle, stretching across vast expanses measuring thousands of kilometers. These regions earn their moniker because seismic waves, particularly shear waves, traverse them at a slower pace compared to the surrounding mantle material. This discrepancy in wave velocity arises from variations in temperature, composition, or a blend of both factors. To grasp the essence of LLSVPs, envision Earth as a stratified sphere. At its core lies the central nucleus, encased by the mantle, which in turn is sheathed by the crust. The mantle, an expansive expanse of hot, partially molten rock, undergoes gradual movement. Seismic waves, generated by earthquakes or similar events, traverse these layers, furnishing scientists with invaluable insights into the Earth's inner workings. Situated near the boundary with Earth's outer core, large low-shear velocity provinces, LLSVPs, are found at the base of the mantle. Notably, two colossal structures stand out. One beneath Africa, dubbed the African LLSVP, and another beneath the Pacific Ocean, known as the Pacific LLSVP. These formations hold significance as they influence the flow of material within the mantle, thereby impacting crucial processes such as mantle convection and plate tectonics. The African province, with an age spanning tens of millions of years, stretches across thousands of kilometers, characterized by distinct, well-defined boundaries. Positioned between Earth's outer core, consisting of hot molten iron, and the cooler, stiffer mantle, this dense structure is thought to disrupt the flow of molten iron crucial for generating Earth's magnetic field. Consequently, these rock formations can precipitate a significant weakening of the magnetic field intensity. Furthermore, the movement of liquid iron within the outer core impels Earth's magnetic axis to tilt roughly 11 degrees relative to its rotational axis. Unlike the stable geographic poles, Earth's magnetic poles exhibit a propensity to wander and alter their positions over time. Scientists postulate that this inclination in the magnetic axis plays a role in the attenuation of the magnetic field, potentially attributing to the phenomenon known as the South Atlantic anomaly. Another contributing factor to this area of diminished magnetic field strength relates to the Sun's discharge of charged particles and plasma. Upon encountering Earth's magnetosphere, these solar materials become ensnared within two torus-shaped belts encircling the planet, famously known as the Van Allen belts. Within these belts, the particles are constrained to follow Earth's magnetic field lines, oscillating between the poles in a bouncing motion. The innermost belt commences approximately 400 miles or 645 kilometers above Earth's surface. Ordinarily, this setup serves to maintain a safe distance between the charged particles and our planet, as well as its orbiting satellites. However, during exceptionally powerful solar storms, the Van Allen belts can undergo significant energization, causing distortions in the magnetic field and facilitating the intrusion of charged particles into the atmosphere. As per a study, in such circumstances, a localized magnetic field with reversed polarity might intensify within the South Atlantic anomaly region, leading to a markedly diminished field strength compared to its surrounding areas. Currently, various theories attempt to elucidate the magnetic field anomaly observed on Earth, yet numerous enigmas endure. For instance, findings from a 2016 study unveiled that the South Atlantic anomaly is steadily shifting in a northwesterly trajectory. Moreover, the anomaly isn't just in motion, but is also cleaving into two distinct entities. Recent satellite data from the European Space Agency in 2020 disclosed that the South Atlantic anomaly is undergoing a bifurcation, manifesting as two separate focal points of minimal magnetic intensity. Although the South Atlantic anomaly, SAA, doesn't seem to have a significant impact on life on Earth, it presents a considerable obstacle for satellites and spacecraft navigating through the affected zones. Because of the diminished magnetic field strength in this region, these instruments are at heightened risk from solar-charged particles, which can lead to severe short circuits and operational malfunctions. The International Space Station, ISS, traverses through the anomaly region, and while its interior and occupants are adequately shielded, certain instruments mounted outside the ISS face potential disruptions. One such instrument, the Global Ecosystem Dynamics Investigation (GEDI) mission, is particularly susceptible to interference from the South Atlantic anomaly, leading to significant data loss and potential damage to critical components. To mitigate these risks, operators often have to shut down spacecraft systems preemptively before entering the anomaly zone. Therefore, close monitoring of the anomaly remains imperative to safeguard space missions and their equipment. The South Atlantic anomaly isn't a recent phenomenon. According to some studies, it's been a recurring magnetic event impacting Earth for roughly 11 million years. This suggests that the SAA isn't necessarily linked to the reversal of Earth's magnetic field, which can happen as frequently as every 10,000 years, or as rarely as every 50 million years or longer. Despite this knowledge, many aspects of the anomaly remain shrouded in mystery. Given the significant and peculiar transformations it's currently undergoing, closely monitoring the SAA becomes paramount. NASA is actively engaged in this endeavor, closely observing this intriguing phenomenon. Thank you for watching. Remember to subscribe for more videos on the latest in the world of space exploration.